Sharing a common neutral on a 3-wire circuit with a bathroom heat mat that has a built-in ground fault circuit interrupter, or GFCI, should not present any problems. Ground fault circuit interrupters are specifically designed to protect against electrical shock. They accomplish this by interrupting the circuit when a ground fault is detected. The GFCI is designed to trip if it identifies a difference between the current flowing in the hot and neutral conductors. This protection remains effective even if the neutral conductor, often referred to as the common, is shared with other devices on the circuit. Regarding sharing a common neutral on a 3-wire circuit with small motor loads, such as a refrigerator or a garbage disposal, there is a potential for complications. Specifically, it could lead to false tripping of the circuit breaker. This is more likely to occur if the motor starts under a heavy load. Motors typically exhibit a high inrush current during startup. This inrush can momentarily overload the circuit. If the overload is significant enough, it can cause the circuit breaker to trip, even though the overall load might be within the circuit's capacity under normal operation. However, if the motor load is relatively small, for example, less than 1/2 horsepower, and the circuit is appropriately sized to handle the expected loads, it should generally be able to manage the inrush current without causing the breaker to trip. To summarize recommendations. Firstly, for bathroom heat mats equipped with a built-in ground fault circuit interrupter, it is generally acceptable to share the common neutral off a 3-wire circuit. The ground fault circuit interrupter will provide adequate protection against electrical shock. Secondly, for small motor loads, it is advisable to consider using a dedicated circuit to supply power to motor loads. This practice can help prevent false tripping of the circuit breaker due to the inrush current experienced during motor startup. Thirdly, if sharing a common neutral is deemed necessary or practical, ensure that the circuit is properly sized to accommodate the combined load of all devices sharing the circuit. Additionally, verify that the motor load is relatively small to minimize the risk of overloading the circuit during startup. Understanding circuit loading and motor characteristics is crucial for safe and reliable electrical installations. When dealing with electrical circuits, several factors must be considered to ensure safety and prevent issues such as false tripping. Firstly, proper wire sizing is essential. The conductors must be adequately sized to handle the anticipated load. This involves calculating the total current draw of all devices connected to the circuit and selecting conductors with an ampacity rating sufficient to carry that current safely. The National Electrical Code, or NEC, provides tables and guidelines for determining appropriate wire sizes based on ampacity and insulation type. Secondly, overcurrent protection, such as circuit breakers or fuses, must be properly sized to protect the circuit from overloads and short circuits. The overcurrent protection device should be rated to trip at a current level that is below the ampacity of the conductors but above the normal operating current of the circuit. This ensures that the circuit is protected from damage in the event of an overload or short circuit. Thirdly, grounding is a critical safety measure. All metallic enclosures and non-current carrying metal parts of electrical equipment must be properly grounded to provide a low impedance path for fault current to return to the source. This helps to prevent electrical shock hazards and ensures that overcurrent protection devices will trip quickly in the event of a ground fault. Fourthly, ground fault circuit interrupters provide an additional layer of protection against electrical shock. GFCIs are designed to detect ground faults, which occur when current leaks from the circuit to ground. When a ground fault is detected, the GFCI quickly interrupts the circuit, preventing electrical shock. GFCIs are typically required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Fifthly, when dealing with motor loads, it is important to consider the motor's starting current. Motors typically draw a much higher current when they start up compared to their normal running current. This inrush current can cause voltage dips and potentially trip circuit breakers if the circuit is not properly sized. To mitigate this issue, it may be necessary to use a dedicated circuit for the motor or to use a motor starter with reduced voltage starting capabilities. Sixthly, voltage drop is another factor to consider. Voltage drop occurs when the voltage at the end of a long circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction and can also increase the risk of overheating. To minimize voltage drop, it is important to use conductors of adequate size and to keep circuit lengths as short as possible. Seventhly, when sharing a neutral conductor on a multi-wire branch circuit, it is important to ensure that the neutral is properly sized to handle the anticipated neutral current. In some cases, the neutral current can be higher than the current in either of the hot conductors, especially if there are significant nonlinear loads on the circuit. Eighthly, arc fault circuit interrupters are designed to protect against arc faults, which are dangerous electrical conditions that can cause fires. GFCIs detect arc faults by monitoring the current waveform and looking for patterns that are characteristic of arcing. When an arc fault is detected, the GFCI quickly interrupts the circuit, preventing a fire. Ninthly, electrical panels and distribution equipment must be properly labeled and maintained to ensure safety and facilitate troubleshooting. Circuit breakers should be clearly labeled to indicate the loads they serve. Additionally, regular inspection should be conducted to identify any potential hazards such as loose connections, damaged wiring, or corroded components. Tenthly, it is important to follow all applicable electrical codes and standards when installing and maintaining electrical systems. The National Electrical Code, or NEC, provides comprehensive guidelines for safe electrical installations. Local codes and regulations may also apply and should be followed. These factors, combined with a thorough understanding of electrical principles and best practices, are essential for ensuring safe and reliable electrical installations. Remember to consult with a qualified electrician if you have any questions or concerns about electrical safety. When dealing with three-wire circuits and shared neutrals, several specific considerations come into play. Firstly, understanding the basics of a three-wire circuit is crucial. A three-wire circuit typically consists of two hot conductors, a neutral conductor, and a ground conductor. The two hot conductors are typically 120 volts each with respect to the neutral, and they are 180 degrees out of phase with each other. This allows for both 120 volts and 240 volts loads to be served from the same circuit. Secondly, the neutral conductor in a three-wire circuit carries the unbalanced current. The unbalanced current is the difference between the current flowing in the two hot conductors. If the loads on the two hot conductors are equal, the neutral current will be zero. However, if the loads are unequal, the neutral conductor will carry the difference. Thirdly, it is important to properly size the neutral conductor in a three-wire circuit. The neutral conductor must be sized to carry the maximum unbalanced current that is likely to occur. The National Electrical Code, or NEC, provides guidelines for determining the appropriate size of the neutral conductor. Fourthly, shared neutrals can create the potential for overloaded neutral conductors. If multiple circuits share common neutral, the neutral conductor can become overloaded if the combined unbalanced current from all of the circuits exceeds the ampacity of the neutral conductor. This can lead to overheating of the neutral conductor and potentially cause a fire. Fifthly, it is important to avoid connecting multi-wire branch circuits to handle tie breakers. Multi-wire branch circuits should be connected to individual single-pole circuit breakers or to a two-pole circuit breaker that disconnects both hot conductors simultaneously. This helps to prevent the possibility of one hot conductor being energized while the other is disconnected, which can create a shock hazard. Sixthly, when working with three-wire circuits, it is important to use a voltmeter to verify the voltage between the hot conductors and the neutral conductor. This helps to ensure that the circuit is properly wired and that the voltage levels are within acceptable limits. Seventhly, it is important to follow all applicable electrical codes and standards when installing and maintaining three-wire circuits. The National Electrical Code, or NEC, provides comprehensive guidelines for safe electrical installations, including requirements for three-wire circuits. Eighthly, when troubleshooting three-wire circuits, it is important to systematically check each component of the circuit to identify any potential problems. This includes checking the circuit breakers, the wiring connections, and the loads connected to the circuit. Ninthly, it is important to use properly rated and listed electrical components when working with three-wire circuits. Using substandard or counterfeit components can create a safety hazard and can also lead to equipment failure. Tenthly, it is important to be aware of the potential for harmonic currents on 3-wire circuits. Harmonic currents are currents that are at frequencies that are multiples of the fundamental frequency, such as 60 Hz. Harmonic currents can cause overheating of the neutral conductor and can also interfere with the operation of sensitive electronic equipment. These considerations are essential for ensuring safe and reliable operation of 3-wire circuits with shared neutrals. Always consult with a qualified electrician if you have any questions or concerns about electrical safety. Additionally, when considering specific appliances or devices, the following points are relevant. For bathroom heat mats with ground fault circuit interrupters, the primary concern is ensuring that the GFCI is functioning correctly. The GFCI should be tested periodically to verify that it is able to detect ground faults and interrupt the circuit quickly. If the GFCI fails to trip when tested, it should be replaced immediately. For small motor loads, the primary concern is managing the inrush current. As mentioned earlier, motors typically draw a much higher current when they start up compared to their normal running current. This inrush current can cause voltage dips and potentially trip circuit breakers. To mitigate this issue, it may be necessary to use a dedicated circuit for the motor or to use a motor starter with reduced voltage starting capabilities. Additionally, it is important to ensure that the motor is properly grounded. A properly grounded motor will provide a low impedance path for fault current to return to the source, which helps to prevent electrical shock hazards. When dealing with appliances that have electronic components, it is important to be aware of the potential for harmonic currents. Electronic devices such as computers, televisions, and LED lighting can generate harmonic currents that can pollute the electrical system. Harmonic currents can cause overheating of the neutral conductor and can also interfere with the operation of other electronic equipment. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters. In addition to these specific considerations, it is important to follow all manufacturers' instructions for installation and operation of electrical equipment. The manufacturer's instructions will provide important information about proper wiring, grounding, and overcurrent protection. Ignoring the manufacturer's instructions can create a safety hazard and can also void a warranty. Finally, it is important to remember that electrical work can be dangerous. If you are not comfortable working with electricity, it is best to hire a qualified electrician. A qualified electrician has the training, experience, and tools necessary to perform electrical work safely and correctly. The National Electrical Code, or NEC, Section 210.4 covers multi-wire branch circuits. This section outlines the requirements for installing and using multi-wire branch circuits, including the requirements for neutral conductors and overcurrent protection. Specifically, NEC 210.4 addresses the general requirements for multi-wire branch circuits, stating that they shall originate from the same panel board or distribution equipment and that they shall supply only line to neutral loads. NEC 210.4b covers the requirements for ungrounded conductors, stating that all ungrounded conductors of a multi-wire branch circuit shall have the same voltage between them. NEC 210.4c addresses the requirements for neutral conductors, stating that the neutral conductor of a multi-wire branch circuit shall be sized to carry the maximum unbalanced load. NEC 210.4d covers the requirements for identification, stating that multi-wire branch circuit shall be identified at the panel board and at each outlet where the neutral conductor is accessible. NEC 210.4e addresses the requirements for disconnecting means, stating that multi-wire branch circuits shall have a disconnecting means that simultaneously disconnects all ungrounded conductors at the panel board. In addition to NEC 210.4, other sections of the NEC may also be relevant to multi-wire branch circuits, depending on the specific application. For example, NEC 210.20 covers overcurrent protection, NEC 250 covers grounding and bonding, and NEC 310 covers conductors for general wiring. It is important to consult the NEC and other applicable codes and standards when installing and maintaining multi-wire branch circuits. These codes and standards provide comprehensive guidelines for safe electrical installations.